Planet Earth, with its many mysteries and nuances, provides an enormous arena ripe for investigation. For problem solvers ready to sort through the intricate web of the past, Earth's surface provides a dynamic laboratory. The science of the Earth is a fascinating subject that encompasses Earth's origin, history, and dynamic forces. Geoscience, with its many subspecialties and job opportunities, is an enormously attractive field for men and women who are curious about the Earth and enjoy working outdoors. As geologists explore Earth's mysteries, examining ancient clues left in the rocks, their findings are categorized into giant chunks of time known as geologic eras. To get a better idea of how all this fits into the big picture, 3 Earth scientists, Marjorie Chan, Sue Halgadal, and Genevieve Atwood, will walk us through 4 major chunks of geologic time. Because to humans the Earth is very old, geologists divide up the major part of geologic time into large bites, called eras. Like a clock, these eras can be compared to a 24-hour day, with the formation of Earth at midnight and today occurring 24 hours later. About 4.6 billion years ago, our Earth coalesced from part of the gas and rocky fragments of the primitive solar system. This was the beginning of what geologists call the Precambrian era. We can think of the Precambrian era as beginning at midnight on Earth's clock. It is remarkable that the Precambrian era makes up over 87% of the present age of our Earth, and during this first billion or so years, there was no life. At about 9:12 p.m. on Earth's clock, approximately 538 million years ago, began the Paleozoic era. The start of the Paleozoic era is now famous for its huge explosion of complex life in the oceans, the most well-known organisms being trilobites. At about 10:43 p.m., approximately 245 million years ago, was the start of the Mesozoic era. This era is often called the Age of Reptiles, or the Age of Dinosaurs. At about 11:39 p.m., approximately 65 million years ago, began the Cenozoic era. This era is commonly called the Age of Mammals, which now includes human beings. This is Utah, beachfront property some 1 billion years ago in the Precambrian era. Tides swept in and out, layering the shallow seafloor with grains of sand. Days were shorter then. Each day the tides would come in, the tides would go out, repeating the cycle over and over. Weak tides left behind fine particles of silt and clay in dark, muddy layers. Strong tides left new layers of white sand and dark silt. Understanding ancient history from these clues found in rocks is the type of detective work driving sedimentary geologist Marjorie Chan.
Okay, see you guys at lunchtime. Bye. Have a good day.
Hey guys, let's go.
Recently, one rock added a new piece to Earth's fascinating geologic puzzle.
These rocks are from some of the oldest of our geologic time scale. It's from the Precambrian era, and that's the time before most multicellular organisms and hard parts and skeletons evolved. So there's very little life forms at this time. These different lines or laminations are what we call tidal rhythmites and tell us about tides about 1 billion years ago. The white lines indicate the strong tides that could carry some of the coarse sand grains. The dark lines indicate some of the mud, which was carried by the weaker tides. And together these indicate daily rhythms, and so it's a little bit like counting tree rings. We can count how many days were in a month, how many months were in a year. Back in the Precambrian, there were more days in a year, and so the Earth was spinning faster. But over time, the Earth has slowed down its rotation and the gravitational attraction. So the moon has been moving away at a rate of centimeters per year, and maybe in another 1 billion years, the Earth and the moon distance will be another 24,000 miles more. I study sedimentary rocks, and those are ones that form at the Earth's surface temperatures and pressures. They go through the cycle of erosion and weathering, transport, and then deposition. These are some of the most common rocks that we find on the surface, and these are important because they contain many of the Earth's resources as well as the history of life. On a typical day, I go out looking for certain structures within the rocks. I often take a rock hammer with me and crack open some of the weathered surfaces to look at what the structures are on an inside or fresh surface. I'll also use a hand lens to take a closer look at some of the structures. I can use a compass to take different measurements on directions. This might tell me which way the water or the wind was moving or flowing at a certain time. I take down some of these measurements in a notebook, and this helps me remember some of the things that I've seen out in the field. When we're out in the field, we try to pick up representative samples of the rocks that we're looking at, and on the outside they're kind of weathered and they might not look very exciting, but we can cut them open and see what they look like on the inside. From here we can take the glass slide and look at it under the microscope, as I have here, and we can see some of the individual grains that make up this particular rock. The different grains have different optical characteristics shown by different properties of light.
We're now going to jump forward in time to the Paleozoic era, which began about 538 million years ago. For geologist Sue Haugadal, this era is especially fascinating as some of the earliest forms of life can be found in today's fossils.
Good, split. Well, earth science involves many things. It involves going out in the field and collecting rocks. It involves analyzing many properties of those rocks back in the laboratory and working up the data on a computer. So we have many goals. Some earth scientists look for mineral resources. Others try to figure out ancient geologic environments. And other people try to figure out how the deep interior of the earth works in a very fundamental way. This is one of my favorite spots, the West Desert of Utah, and here you can really see the bones of the earth. Even though this is now a desert, about 520 million years ago, this was all covered with ocean that was teeming with life.
Well, about 10 million years before these rocks were laid down, there occurred one of the most remarkable and rapid explosions of evolution that this earth has ever seen. And the plants and animals that evolved at that time in those seas were preserved in the rocks like this trilobite. By studying fossils such as these, scientists hope to learn how ancient life evolved from very primitive forms, and this includes human beings.
For Marjorie Chan, interest in the sedimentary process includes not only the Precambrian era, but the Mesozoic as well. This magnificent, multicolored landscape contains valuable clues for interpreting the ancient environment of the Earth. Each distinct layer is expressed by color, composition, texture, erosion, and weathering. Understanding how this ancient desert with its blowing, shifting sand captured history within its rocks is another piece to the giant geologic puzzle. For geologists, these structures hold valuable clues about what the wind, depositional environments, and general climate conditions were possibly like 100 million years ago.
What a spectacular and great view here. I just love being able to understand the landscape that we see around us. And here we have over 250 million years of history that's preserved. You can think of the layers much like layers of a cake. Each layer represents a different environment, a past time in geologic history. Many of those were laid down and then buried, and then over time those eventually were raised up or lifted up again. And the river is much like a knife cutting through the layers of a cake. It's been raised up so much that the river is deeply incised down to expose much of the beautiful strata that we see here today. Moving water is a powerful agent of erosion. Water is collected in the mountains, carried by the rivers, where it erodes and cuts down, and eventually carries the particles out to the sea. This creates the beautiful landscape that we see.
Many of these layers contain more stories of life history. This Mesozoic period, known as Middle Life, is commonly called the Age of the Reptile, conjuring up images of dinosaurs that capture our imagination.
The rocks that are exposed around us are from the Mesozoic era. This is part of the geologic time period, which is referred to as Middle Life, sometimes called the Age of the Reptiles. In particular, the animals that stick out in our minds are dinosaurs. In these particular rocks, we have several footprints that are preserved, some of the sauropods that probably stepped and made deep impressions in the sand. This was a plant eater or an herbivore. This is what we call a trace fossil. A fossil is evidence of pre-existing life, but in this case we don't have the direct evidence of bones or a skeleton. What we have is some indirect evidence, or essentially what we call a trace or a footprint. In this case, we have an example of a three-toed dinosaur. It was probably a meat-eater or a theropod that stepped in the sand and left an impression. Sometimes these impressions can also be found in conjunction with a cast. That is the material that filled in. Here's an example of a cast, the three-toed dinosaur footprint, although not exactly from this particular example, but you can see the nice preservation of these three toes, and you can imagine how this cast might have fit right back into the impression.
The study of these landforms and life is not just an ancient story from the distant past. We find dinosaur remains in these rocks, and we also find the energy resources used to power the world we live in today.
Here's an example of coal. Coal is made up of compressed plant material, so this 2-inch piece was maybe originally 20 inches of plant material, which has then been compressed over time to make this very concentrated piece of coal. This dark material often occurs in conjunction with rocks that are deposited in marshes or swamps where the coal and the plant material tend to accumulate. This is an example which shows some of the different plant material that you can see preserved in the rocks, right where there are some of these dark lines and dark spots. So oil and gas, as well as coal, are some of the many resources that our society uses for energy. This is a wonderful outdoor laboratory where we can look at some of the many structures that are preserved in the rocks. These rocks tell us that about 190 million years ago, this area was once a vast ancient desert. What I'm sitting on are some deposits that represent ancient sand dunes. Millions and millions of sand grains migrated up the back of a dune and then avalanched down the front. And these different lamina or lines that you can see represent the different deposits at the front of the dune. The immensity of these deposits indicates that these were very large sand dunes. And the wind was a good agent for sorting some of the sand grains. It would make nice little holes in between what we call the microscopic pores. Those would get preserved as these deposits turn into a rock. This is another example of an ancient sand dune deposit. This one is much darker and looks a bit different because of the oil that is trapped in between the sand grains. These kinds of deposits make very good reservoirs for oil and gas, and even for important resources such as water. Our human lifespan is like a millisecond compared to the geologic time it's taken to evolve this beautiful landscape. About 300 million years ago, there was an ancient sea here, and as it dried, it left thousands of feet of salt. Later landscapes came and went. The winds came in and brought some of these ancient sand dunes preserved in these orange rocks you see behind me. Over time, these layers lithified and became rocks and were buried. But the salt underneath would constantly shift with time, and it's a little bit like a tube of toothpaste. Tectonic forces would squeeze, and in the areas where it squeezed up, joints would form in these rocks. These are regularly spaced, repeating fractures in the Earth's crust, and those become zones of weakness. Water works in along those cracks and enlarges them, and what remains are what we call fins, very thin slabs of rock. Over time, water continues to seep down through the rocks, and particularly along certain boundaries, the water tends to accumulate. During the wintertime, the water freezes and the ice expands. During the summertime, it melts. And that continual freezing and thawing over millions of years causes big chunks of rocks to fall out. And over time, more and more erodes at that boundary, leaving these types of beautiful arches you see behind me.
So, I'll head on out to the island. Thank you.
While much of the field of geology is a study of the past, many geoscientists provide tremendous insight into the future, especially when it comes to environmental concerns and global climate change. For geologist Genevieve Atwood, her interest lies in sediments from the Cenozoic era, known as the age of the mammal, and includes the first appearance of hominids. In examining this period of time, from 66 million years ago up to the present, Genevieve often studies material that hasn't become rock yet. Most of her work centers on the Great Salt Lake in Utah, where her specimens may be only 10 years old.
Most people think of geology as something in the past, and in large measure it is. But geology is also about the processes, and it also is a continuum. And so I work very much in the present. My work is really with geologic materials that are only 10 years old. And I'll be quite happy and proud of myself if I figure out the last 10 years. Moving on, next stop. That was number 15. So you walk along here and what do I see? Well, I see what's going to be in the geologic record, which are these rocks. But what's different is this stuff, because that has been human shaped. And I look for that kind of debris in this shoreline, and that dates it as the 1980s. So look at this trash. The advantage that I have in my work is I know exactly where I am in terms of time. Geology in general looks to the past, but it also tells us about the future. And one of the things that a geomorphologist does is in turn link these physical processes with how they affect human beings in terms of natural hazards, floods, earthquakes, debris flows, the suite of problems that we have not just in Utah, nationwide. Well, all geologic eras are interesting, but what's specifically interesting about the Cenozoic is that we live in the Cenozoic. So if you were a dinosaur, you'd care about the Mesozoic the way we as human beings care about the Cenozoic. It's what all the features that you see, all the landscapes that you describe, all the mountains, the valleys, those are called landforms. And they all date from the Cenozoic, at least in Utah. Landforms in general aren't the same ages of the rocks they're made of. So this rock here is about 500 million years old. But the island has been around a maximum of, let's say, 25 million years old. And behind us, of course, are these sediments, that some of which are just maybe a day or 2 or 5 days old in terms of when they got where they are. So the Cenozoic is where we live. It's also where you can look and see the processes that are going on the surface of the earth. The Great Salt Lake is the lowest point in our basin. It has no place to flow out from. So it captures everything. It captures the water comes in, also captures the sediments. So it's capturing the story. And in these days when we're so interested in global climate change, Great Salt Lake is the historian. And so, yes, you see the story of the shorelines as you march up and down the hillsides here, but you go out in those muds, you put down a core, you get a continuous history of what has been going on year by year. And for a geologist to find sort of a storybook like that, Great Salt Lake. Okay, off we go. So, hard day's work, don't you think?
Find anything?
Found this piece of limestone with some little stromatolites in it.
Most earth scientists would agree the most enjoyable part of their work takes place in the field. But field work must be backed up by careful lab work, using the latest technologies and computers. Much of Sue's work involves studying the ancient magnetic signals locked in rocks. Here, in the Paleomagnetism Laboratory at the University of Utah, Sue works with the magnetometer.
It's a remarkable fact that our Earth has an associated magnetic field. You can think of the Earth as like being a big bar magnet. It's also remarkable that when rocks are laid down, they record the direction of the Earth's magnetic field at the site where they're emplaced. So in a very real sense, rocks act like very, very weak magnetic compasses. We can think of the Earth as an apple. And the ground that we walk on, the continents, and even the rocks that make up the ocean basins, are a very, very thin skin that covers this much, much larger apple. Now this skin is broken up into about 10 different pieces. And these pieces are called the tectonic or lithospheric plates, and they move around with respect to each other in various ways that have changed over time. When a rock is laid down, originally, it becomes magnetized in the Earth's field. And you can think of that magnetism as an arrow that points toward magnetic north. But because the plates move around on the surface of the globe, these arrows move with them. So in other words, imagine my finger as being the magnetic arrow within a rock that originally pointed to magnetic north when the rock was laid down. Now, imagine this arrow moving around with the plate like this. Okay? The arrow is fixed with respect to that plate, but it moves around with respect to magnetic north. We can track the way that these arrows on a particular plate have moved with respect to time, and therefore we can track the plate motions. And this is what's called the science of paleomagnetism. One of the instruments I use is called an alternating gradient field magnetometer that we nickname the micromag. And what this machine does is that it measures little tiny chips of rock, sometimes less than a millimeter in diameter, and gives us all kinds of magnetic properties that help us judge whether that rock made a good paleomagnetic recorder or not. The instrument is interfaced to a computer, and so all the data that we're generating streams over to this computer right over here, and the data are displayed on the screen. And in this particular case, I run a sample that would probably make an excellent paleomagnetic recorder of the plate motions in the past.
One of the things I really love is mysteries and trying to solve maybe what happened at the scene of the crime. And looking at rocks is a little bit like that because you're looking for different kinds of clues. Sometimes clues are important, other times they're not so important, and sometimes the collective group of clues tells you what environment or what's happened millions of years ago. So it's a lot like a detective trying to figure out what clues are important and how to put them back together. One of the things I like about my job is being outdoors and being able to enjoy the surroundings around me. I like sort of the variety of being away from the office and the desk, and also the chance to travel to different places. Sometimes I get to take my family on trips with me, and we can enjoy things together and meet back for lunch while I'm doing field work. Oh, was it from the stream?
Yeah.
Maybe it was polished in the stream.
We're too close to the soil line.
Well, geology is like a giant treasure hunt. Sometimes you set out to find one thing, but you end up finding something totally different that's even more interesting and even more exciting. Oh yeah, wow, look at that. Boy, that's like a kill zone, like a mortality zone. Look at look at all these little, oh, that's great. Can you find the rest of that, Dave? Where'd that come from?
Somewhere up here, but
that's great. Man, look at all those guys.
For those interested in learning more about our planet, the Job Outlook promises a variety of career opportunities ranging from fundamental research to practical areas such as resource exploration, environmental engineering, and even politics.
You know, geology is really an exciting field because it combines math, chemistry, physics, as well as biology.
My advice to anyone thinking about becoming an earth scientist is take lots of math, enjoy it, think of it as a language. It's the language of science.
Geology, like all sciences these days, is a high-tech field. But on the other hand, remember that there are so many specialties available that there's something right for everyone.
The Earth still has some mysteries and puzzles that we haven't yet solved. One that I've been fascinated by are some of the contorted layers that are in the interval just below the arches. What form those contortions? Most people would come out here on a vacation for a few hours to ponder how these might have formed. But in my work, I might spend several days out here measuring detailed sections of the rock, spending several weeks in different areas.
Without a doubt, the reason I entered the earth sciences was because of fossils. When I was about 9 years old, I was told that ancient organisms were sometimes preserved in ancient rocks. These are called fossils, and I immediately wanted to go out and find some. And eventually, I did find some, in fact, right here in Utah. Somewhat later, I became interested in physics, and so it's no surprise that eventually I combined physics with geology and became a geophysicist.
Look at where I get to work. I mean, my laboratory is outside. Life is my field trip. And how many people can get paid when they're eating lunch on an outcrop or have their dog as a field assistant, welcome at work anytime? Geology is a joyous profession, particularly for folks who like to work outside. For those of us who do, there's nothing better.